All right, it is 2:40, so we should get started. We have a lot to cover today, as we always do. But what are we talking about today? It is on the last day of Module 2. So after today, we're going to be done with the parsing, and we're going to essentially be taking what we parsed, and we're going to be putting it into other structures to help us get down closer and closer to machine code. So today we're sort of wrapping up this part of the compiler and moving on to the next part, which I think is quite exciting. So today we're going to review a little bit of that recursive descent parsing that we talked about. That is essentially going to be your homework 3, which is aimed to be out by midnight tonight. And then we're going to talk about symbol tables a little bit, which I think are an interesting part of parsing. Some people... Symbol tables sort of exist at the intersection between parsing and the next step of the compiler. So I think now is a good time to do it. And if it's time, we'll talk a little bit more about parser generators. So, as always, let's start with some announcements. So homework 2 is due tonight by midnight. So for help, at the time when I wrote these slides, Ant still had the office hours, but then he had a plan that he had made quite a while in advance. He's not going to be able to have the office hours, but we will strive to have every question answered that is posted before 5 o'clock. So if you have questions on the homework, please ask them on Piazza, and we will have a look at them. And yeah, just remember there's no guaranteed help over the weekend or off business hours. So, I've tried to make sure everything is answered pretty timely today, and I'll keep doing that up until 5 o'clock. So for part 3, there's been some questions on this. For the follow sets, we've already kind of given away what we're using the follow sets for, is we're going to use the follow sets to build a recursive descent parser. So for the follow sets, you need to be able to build the first plus set. You don't need to do that in the assignment. The assignment just asks for the follow set. But because of that, you only need follow sets for rules that have the empty string in their first set. The follow set's technically defined for any non-terminal, but you don't really need it because it's only really useful when you have the empty string in the first set. So this is the only case where you actually need to do the follow set, and then when you combine those, that gives you the first plus set, which you use for parsing. We haven't changed the autograder, I think, since Friday, and it was pretty stable before that. So thanks to everybody who's worked with us, but the autograder's in pretty good shape now. We've added a few test cases to Gradescope. So these are test cases that will kind of check to see if you're along the right path. We're not showing the test cases. It's for you to kind of help guide you as you write your own test cases to test this grammar. We haven't added anything since last time. This is just there. Like I said, designing grammars, asking questions about the grammar, asking questions about strings that you think are valid programs or what they should be. It's all part of the process. And like I said, it's fine to discuss individual test cases on Piazza. Like I said, it's part of the process to ask questions, to try to think about how this description of a language in English actually turns into a formal grammar, how it relates to a programming language. And because that's part of the process, I want to give us time to actually talk about some questions. If people have questions about the homework in general, or about what program should be allowed, what program should be disallowed. Yeah, does anybody have any questions that they want to talk about? Yep. Right.
Then before it needs a semi in it, but my assign statement also already had a semi. So on the next thing after, was looking for another semi, I couldn't find it.
Yes.
I was wondering, I could remove the first semi, but the last assign statement doesn't need one, or shouldn't have one. Maybe I don't. It might just be optional for that one. But how would you handle keeping or removing that semicolon at the end of the assign statement?
Yeah, and that's pretty interesting, right? Because we have our for loops that we're used to writing, like for I, if it stops auto-capitalizing, for I equals 0, I is less than something like size, I plus plus, close. And so, yeah, what you're, if I'm understanding correctly, this is an assignment statement, and it ends with a semicolon. So that one kind of works. This is an expression. And so, you have to explicitly add the semicolon to the end of that one because expressions are typically parts of assignment statements. So add the semicolon there. And then this is interesting because we're used to writing things like I++. But does C simple, does it allow I++? No. So instead, what does I++ really mean? I equals I plus 1. It's an assignment statement, and we do handle assignment statements. So there is an assignment statement here. But the difficult thing is that, in C, there's no semicolon here. Like, I think the compiler wouldn't even like it if you tried to put one. So, yeah, how do we handle this? How have people handled this in theirs? Yep.
I have our normal assign, and then I have another production rule called nassign, which just doesn't include the semicolon, and I only use nassign with the for loop.
Yeah, so I think that's one way how to do it. It feels a little bit hacky, right? But I think it's a perfectly valid way how to do it. Yeah.
The way I solved it is I just made it so that when defining statements, you just add a semicolon for I think the sign and like a declaration over the other one, and then everything else that came before doesn't even matter.
Interesting. And that seems to work in your test cases. Yeah, it sounds like it works. So there's a few ways how to do this. And yeah, there are these little discrepancies that you do need to think about. And like I said, ultimately, we want this to be fairly faithful to C. So, but one thing we don't handle is we don't have to worry about having int there. And the reason why we don't have to handle that in our grammar is because that essentially combines this declaration with an assignment. Now, it's very nice that C and C++ allow us to do this. I mean, we probably write code like this all the time. I do it as well. But as like a little history lesson, that used to be disallowed in early versions of C because early versions of C didn't want you combining declarations with assignments. And so, we're going back to early versions of C, and we're not allowing that because combining declarations and assignments, it's going to make things just a little bit more tricky in the future. But, keep that in mind that as we make the language simpler for us to parse, maybe we're taking away some of the features that you might really like in the language. Yep.
Yeah, sorry, just one. I was just wondering, so for I guess an if statement maybe will make more sense. In an if statement, because I have an expression production rule that allows me to use expression in parentheses.
Yeah.
So my if statement theoretically could have just been if expression, and then it would have found the parentheses through the expression rule. Would that then allow people to avoid the parentheses then and try and navigate around them if they're not forced in the if production rule?
Yeah, that's a good question. But you're saying that your expression has the option to put parentheses around it, right? Yeah, because you don't want to allow like if I is greater than 10, right? So if those parentheses have to be there explicitly, then yeah, you want them there. Yeah, because this is the part of the compiler where you want to be able to catch errors like this and to alert the programmer that something's off there.
Okay, this is
Yep.
what builds with syntax.
Yep. Yeah, good questions. Yep.
Yeah, so for the for loop, if the person puts a semicolon after I equals I plus 1, would that be allowed in the grammar? It said it wasn't required in the spec PDF, so I wasn't sure.
Yeah, so we want to stay faithful to C. So let's see what C does. So to do that, we can come over here. That's as a demo for later. If we have for, let's declare int I. Let's say I equals 0. I is less than 10. I equals I plus 1. And then if we do a semicolon there, it looks like we are failing. Let me just put an empty body. Yeah, so C doesn't like the semicolon there. And what we want is we're not going to handle everything that C does, but we want C to be able to handle everything that we do. So we want that one-way compatibility there. So, yep, this should be disallowed. Yep, don't have that semicolon. And, I think this goes to sort of the difficulty. Like, when you're describing a grammar in English, sometimes you have all these corner cases that you need to specify somewhere. And it's hard to do it in English in a way that makes sense. So yeah, talking about this and asking questions. Yeah, I think that's part of the process. Anyone else? Yep.
So assignment should not be having a type and an ID and then the equal sign and then the expression?
Yeah, so in our grammar, we don't need to handle int x equals 10 because that's combining an assignment statement with a declaration. And in fact, in old versions of C, you wouldn't be able to do this either. This is sort of a, when I say newer, I mean maybe in the last 10 years. So, what is this called? I guess I would just call it kind of declaration and initialization. But we don't have to support it. You can if you want. Like I said, you can feel free to add whatever you want to the language as long as it's backwards compatible with C. And if you understand that if it makes the autograder mad, you might have to come see us in office hours. But feel free to think about these extra things that we're not handling and how you might. Yep.
So to be clear, if I add an increment like plus plus, I don't have to go back and remove it?
No, but like I said, you might have to come see us in office hours. But we want you to explore with stuff like that. Yeah. Camden?
I actually supported this, and then when I got to making my first sets, it was no longer predicted.
Yes. So be careful with that, because part of the way that we've designed this grammar is so that when you get to getting your first sets, that they're going to be disjoint. So you need to make sure that your first plus sets stay disjoint. So yeah, good point. Laura?
For the photo sets, how do we represent the end of file? Is it like none and the slides?
It's none, yep, because that's what your Lexa returns. Remember from homework 1? In homework 1 with your scanner, that's what we're eventually going to be using. And when it's done tokenizing, it returns none. Yeah.
Also, you said in the examples that if there are not, like if there are not any strings in the first set, then the photo set should be empty and we represent that as
Just braces, empty set like that.
even because in the initial code, all the photo sets have
Yeah, it's just like that to illustrate how to fill them in. But yeah, you just have an empty set like that. Yeah, cool. All right, so a question I like to kind of throw out to the class around this point of the assignment, and maybe some of you have been thinking about it as well, thinking about expanding this grammar to be a richer set of C, what would you have to change in the grammar to support else ifs? What would you do to do else ifs? Can anybody think of kind of what the first step there would be? Do you need new tokens? James?
Are you saying if you wanted like just ifs and then also if else's?
Yeah, if you wanted something like if, else if, else, something like that. Yeah, do we need new tokens? Yeah?
I think you need new tokens, but you would need a look ahead.
We would need what?
You would need a look ahead.
We might. It seems like we'd need a look ahead, right? Because, you'd have this else here and you'd have this if, and you don't want to get that ambiguous. You're very close, actually, to what I'm thinking. Yep.
Do you need anything? Because an if statement is a statement, and an else is a statement, right?
Yeah.
Well, that would,
Yeah, think about it. Our current grammar says we have if followed by an else, and then following else we have a statement. Well, this is an if statement. So we automatically have else if in our grammar just because of the way the language is set up. I saw some hands. Yeah?
Wouldn't that if statement need to be like solved inside of the first else statement though? That second if statement overall?
This one?
Yeah.
No, I think it's fine, right? The semantics of if are you evaluate this if, you check to see where you go, and then if you go to the else, you evaluate this statement, and then you kind of come down. So I think it's something that's not obvious, but if you spend some time thinking about it, I think it's this very clever thing that just works in the grammar that we're sort of taught to think about as a separate construct, but really it's just if else followed by an if statement. And when you define your statements like this, you get some kind of cool stuff that just falls through. Yep.
No, it's basically the same as if, and then you have else with the curly braces, and you put if inside, and then there's an else right under there.
100%.
That's all it
100%. You can think of it, if it helps your brain to think about it like that, with braces and like indenting it. That's all what an if-else is. This is just adding braces to it. But this might be one of those cases where maybe we don't like to have the braces because it gives us this nice other else-if structure that we kind of are used to seeing. So yes, good comment. But yeah, so I think it's kind of cool that for free, we get else-if statements. Yep.
Just to make sure, I think this is already answered, but for the assignment, this assignment is due tonight.
Mm-hmm.
No such thing as an if by itself.
No such thing as an if by itself. Yep. Every if you have is matched with an else. Yep.
Also, I was just wondering why whenever I get my auto-graded thing, it's always like 80% of the total grade. I don't know if that's like supposed to be a thing.
Did
The other 20% is the write-up.
yeah. So and
It's not, because the other 20% is like 40 points, but then the thing is like, it's like 40 out of 60. When I put my homework in there, it says 40 out of 60, and that's all I get for the auto grade. And then
Okay.
the write-up is at 40 points, and it makes no sense.
okay. Make a Piazza post, and the TAs are focusing on it. Yeah.
I think that's because part 3 isn't auto-graded at all.
Part 3 is not auto graded. Okay.
So there's just like no points for it at all on Gradescope. So it maxes out at 40 out of 60.
Okay. Yeah. Thanks.
Well,
Yeah.
I mean, it also happened in assignment 1 too, so.
Okay. We'll make. Well, we're.
I think those are dirty.
Okay, yeah, make a Piazza post, and it sounds like that's something that others are looking at, so we'll get it. The TAs are in charge of the grade scope, and they're pretty responsive. Cameron?
I'm curious if this just kind of works inherently. Why will you ever implement like elif language?
That is a good question. What do people think?
Faster to type.
It's faster type. Yeah, you save like 3 characters. That's a good. I don't actually have a good answer for that, because yeah, this is for free in your grammar. Yeah.
I can't remember, but I think maybe in Python, like elif, it checks every elif and the first if at the same time, or something like that, or instead of just checking them in sequence.
I see. There might be some interesting semantics things there. Yeah.
Maybe it's because you can't have like an if something without a colon.
Interesting. That could be the case too.
Or else
It's I don't know exactly the reason. We should do some investigation, because that's a very good question. Cool. Anything else? Well, yep.
So for part 3, are we supposed to end up with a predictive grammar, or is that?
Yes, you should have a predictive grammar at the end.
Okay.
Yep.
So as for that, when the for statement, because of the optional semicolon at the end, like doing it in a certain way ends up with a non-predictive grammar, so that usually fits.
No, I think you can still get a predictive grammar out of it, because predictive grammars have to do with your first set, right? And so to match a 4, you have 4. That's your token that you match there. An assignment statement is predictive, and then if you have the optional semicolon at the end, that can just be an optional rule you have, or a separate one. You can factor it in a way to be predictive. Yes, I see your point, but you can get there. Yep.
I wanted to ask for the if state, like just in the documentation, you have it described as an if parenthesis and then followed by a statement.
Yeah.
Our statements should be able to handle block statements, but do we need to enforce those curly brackets?
Yep.
We do.
Well, okay. So in an if you can be followed by any statement you want. A block statement will be curly braces, but you don't have to have is what you're asking. You could have an assignment here. You could have.
But then if you have if else, when you have to use the block statement, or can you still use that cascading way?
I don't think so. I think it still works with the cascading way, because your if statement right here only
It's only the next line.
it only matches to the if, and then your else, like if you don't have the braces, your if, you don't need them here. Your if statement handles that as well.
I see. Yeah. Okay.
Like I said, I think it's not obvious, but if you stare at it for a second, you'll kind of realize that it works, and it's kind of cool that it does. Yeah, good questions. Interestingly, one thing about these for loops is, I know we're used to writing for loops like this, but the middle component of the for loop, it can be an expression. So, could you have like I plus 2? Is that something you could do? Could you do that in like C? Yeah, I don't know why you'd want to, but in C this is a I plus 2. Let's get rid of that semicolon. And in C, that should work just fine. Why isn't it not? Oh, we have a warning, but it compiles. Oops. Okay, so you can have whatever expression you want here. Could you even have a number? Could you have like 1? What would that do? Simon?
Well, if the number was 1, it would loop infinitely, but if it was falsy, then it would.
Yeah, if it's 1, you just never break out. Like 1 is evaluated to true in C. So, hopefully as you're designing this grammar, the rules that we're trying to do are quite similar to C. And, hopefully it's getting you to think about these languages that we use in a slightly different way. Okay. Any other questions? Okay. If not, so on these slides, I put the midterm study guide. We're not going to go over it because we've been over it a few times, but it's just there, so it's easy to find. Let's talk a little bit about the quiz. So for the quiz, we had this grammar. Is this grammar backtrack free as written? Who says yes? Who says no? All right. So how do we actually figure out if it's backtrack free? Max? Yeah, we need to go look in the first sets, exactly. And, how I would do the first sets here is I'd, make a set for each rule, and I'd find the rules that start with a terminal. So here, that one starts with a D, so we know that D is in the first set, because we know that immediately. C is in this one. And then you can sort of go top down a little bit. You can say, well, C, this rule can go to A. Well, what's in the first set of A? We don't have that yet, but we have to go look at B. D is in the first set of B, so we get that one because it's in one of the options. And then we say also C is there. If we go down to C, one of the options has C. And then we'd stop there because this ends up having left recursion, which already is questionable about whether it's predictive. But these are the only characters that can start at the beginning of a production option. Then similarly, you can say C. Well, for this production rule, AC, well, what's in the first set of A? A is DC, so DC there. And then for B, you can say, for this rule, you say, well, what's in the first plus set of C? C is C, D, C, but it's a set, so we just get C and D. Okay, so we can get our first sets. That's not too bad. But then why isn't this predictive? Jacob?
Because the sets for each non-terminal are not disjoint. So if you look at the two sets for non-terminal B, first rule has D, the second one has C and D. D is in both. We don't know which one to pick.
Exactly. So you look at a non-terminal, in this case B. You could have also looked at C, and then you look at their first sets. Ideally, you'd need to have their first plus sets, but there's no rules with empty string, so we can get this. And then what that allows is, if these are not disjoint, what that means is if you are looking at a character and your look-ahead set is D, you don't know which rule to choose. So it's not predictive. You need to have backtracking in that case. Okay, so similarly with this one, Lara? I did what? I see. So if you just go to the URL, and if you change that, I guess last Friday was the 26th. If you change that to 29, it should be there. Yeah, let me know if it's not, because I'm pretty sure I did upload it. Cool. Okay, thanks. always little things, right? Okay, so similarly, you could do the same thing with this one. We're running a bit short on time, so we won't actually walk through it, but turns out that this one doesn't end up being predictive for the same reason. You do the first plus sets, and you find for non-terminal B that these are not disjoint. Okay, so next question. In a recursive descent parser, you make a function for each of what? Do you make a function for each production option? Do you make a function for each context-free grammar? What about non-terminal? And what about terminal? Looks like people aren't exactly sure. That's all right. We did this at the end last time. So, like I mentioned, this is what you'll be doing for your next homework. So, it's good to kind of know what these recursive descent parsers are all about. So here's that simple grammar that we've been looking at. We've gotten rid of left recursion. What you want to do is recursive descent. I know we've had that big, hairy-looking algorithm up here for a while, but recursive descent, we're actually going to get easier. What you say is, how do I parse an expression? Well, if I want to parse an expression, I need to parse a unit followed by an expression 2. So when I make a function, I can say parse expression. All what I have to do is I have to parse a unit, and then I parse expression 2. Again, we're going to be using the magic of recursion here, but it's really, a really nice top-down approach, because then we say, well, if I want to parse an expression 2, how do I do that? Well, I have 2 choices, and to determine which choice I make, I need to go look at our first plus set. So I need to see which token we're currently trying to match. So I'm going to grab that with a token ID, and then I need to look at rule number 2. Well, in the first plus set for rule number 2, I have plus or multiplication. So if that token ID is plus or multiplication, then I pick rule number 2. If I pick rule number 2, how do I parse that? Well, I parse an op, I parse a unit, and then I parse an expression 2. Exactly what the grammar tells me. Now, if I want to pick the next rule, rule number 3, I look at the first plus set. So there's none, which is the end of the file, or the closing parenthesis. So if that's the token that I'm trying to match, then matching the empty string is really easy. I just return. That means I've already matched an expression 2. And then the cool thing is about the recursive descent parsers is if my token that I'm trying to match is none of these, if it's not plus, mult, or right parenthesis, that means that whatever string I have doesn't actually match the grammar, and I can throw an exception. And what I can say is, hey, I have observed this. Maybe I'm looking at a semicolon, but I'm expecting a plus, multiplication, or right parenthesis. We've all seen those compiler errors, right, where they say, hey, I see a number, but I expected a semicolon. That's exactly where you're getting those sorts of syntax errors. Yep?
For a simple non-terminal, like an op, is it impossible for the first plus sets of each production rule to have the same characters?
For ops, pretty easy, right? Because you just have a single terminal. So, yeah, that single terminal just ends up being itself. And you get that way because of the way we designed it. But, yeah, first plus sets end up being pretty easy for those ones. So I'd suggest that you start with those ones in the homework. Laura? First plus set? I guess you could, but the thing is the empty string isn't really useful for parsing, right? Because it's just a blank, it's a freebie. So you're never going to get a token that is the empty string. There's no token for the empty string. So technically it could be here, but it's not really useful here. So a lot of times when we're talking about implementing the parser, we will ignore it in the first plus sets. Okay. Cool. So then, how do you parse a unit? Well, again, we have to look at our first plus sets. If we see an open parenthesis, then we're going to pick rule number 4. If we see an ID, then we're going to pick rule number 5. And we essentially just have this Python function that gets our token ID. We see which one we have, and then we determine what we're going to do. Now, here I have this function I call eat. But essentially what eat is going to do is it's going to make sure that the token we're looking at is a left parenthesis, and then it's going to get a new token. So we're going to eat this terminal, parse the expression, and then eat the right parenthesis. So essentially, when you're parsing production options with terminals, you just eat the terminals. And then, eat, like I said, eat is defined as going and checking that that's the terminal that you want to see, and then calling your lexer.token, which we said returns the next token. Okay. So, yep, sorry.
So in the homework for the set part, should we include for the empty string in the first set the empty quotation marks?
In the first set, yeah. Yeah, do that in the homework.
Okay.
Yep. Cool. It's omitted here for the parsing part. Yeah.
Thank you.
Okay. So the last question on the quiz, and I know we're spending a long time on the quiz today, but it's actually going over a lot of the stuff that's important for the homework and for your next homework as well. So we talked about these LL1 grammars. Let's see if I can remember. It's a left to right, left derivation, one look-ahead symbol grammar. So it has a runtime proportional. So basically these grammars that we've been looking at, the grammars that we're going to parse, when you do send it a string and tell it to parse it, what is the runtime proportional to? Is it proportional to the number of non-terminals? Who thinks that? Well, for each, you could imagine making a massive grammar that just goes down an insane amount of time to non-terminals, and essentially you have to make a function call each time. So maybe the number of non-terminals has an impact on it, but generally speaking, the number of non-terminals we have is going to be relatively small, especially compared to large programs. Is it going to be dependent on the length of the input string? Who thinks that one? Yeah, a few people are saying yes. What about the number of tokens in the input string? A few more people saying that. What about how many times a backtrack might occur? Yeah, a few people saying that one. Okay, well, so one of the takeaways here is when you are LL1, you don't need to backtrack. That's why you have the first plus sets that are disjoint. That essentially tells you for certain which rule that you have to pick. So, in an LL1 grammar, no backtracking, which is kind of the magic of them. So that's why we like LL1 grammars. You could say the length of the input string, because we know that the lexer has to scan the length of the input string to eventually get its tokens. So, I would say there's a good argument for that one. But ultimately, what these grammars do when you parse them, it's a couple of recursive calls, and then you eat the token, and then you eat another token, and you eat another token. And so really, what I think best characterizes the runtime of one of these grammars is the number of tokens in the input string. So, like I said, some arguments for each of these, but I really think that would be the right answer. Okay, any questions or comments before we move on? Okay, so like I mentioned, we're going to do a little bit of symbol tables. So how many people know what a symbol table is? Let's see. Few people have maybe heard the word. Okay, we're going to talk about that, and we're going to now talk about the scope of variables, which is something I know we've all dealt with. We've all tried to access X, and it says X is not in scope. Or we've all accessed X, and it's referred to the wrong X that we didn't want it to refer to. So, yeah, let's talk a little bit about scope. First off, yeah, what is it? What is scope? If you were in a job interview and somebody asked you what scope was. Anybody want to venture? Jacob?
It's where a variable can be seen.
I like that, where a variable can be seen. Yeah?
But similarly, where it can be seen, scope can also include other information, for example, like Rust, depending on the scope, it can also encode, can it be modified within that scope as well, the variable.
Can it be seen? Can it be modified? Ooh, and, Rust has those rules, but Python also has those rules. So, yeah, that gets interesting. Yeah, anyone else want to say what scope is? Yep.
It could also be for things, it's basically just where some piece of data can be accessed, whether that be for reading, writing, whatever. I think that's the most generalized way of saying it.
Yeah, I think so. Yep.
Is scope the same thing as a lifetime for objects?
There might be subtle differences, but I think intuitively it's a similar concept. Yeah. Yep.
Let's say it's the context in which a variable can be applied.
I like that a lot, actually. Yeah, context. Basically creates a context window, and you can whatever's in your context, you can refer to it. Yeah, that's a great definition. Can scope be determined at compile time, or does it need runtime? What do people think? Yep.
Compile time.
Compile time for many of our favorite languages, right? C and C++ and Java and stuff like that. And the reason why those languages need to determine it at compile time is because they need to know what data type it is. You're going to treat an int differently than you treat a float, differently than you treat, I don't know, a class for a cube. So you need to know the data type. You actually need to know what storage, because when we have variables in our programming language, they eventually get mapped down to registers, and you need to know which register you're referring to when you access them. So for a lot of our favorite languages, it's you want to do it at compile time. And in fact, a lot of people who like kind of functional languages or languages like Rust, when you do this at compile time, it helps prevent a lot of errors that you might otherwise stub your toe on. Are there languages, that do it at runtime? That do scope at runtime? What was that? Yeah, Python. Python does everything at runtime, and it's pretty interesting. Does anybody have any interesting scoping rules they know of? This is something that we all seems like very intuitive, and then like you see weird cases, and it gets crazy. Yeah?
I believe in JavaScript, if you use the for keyword, it makes wherever you define it, it makes the variable global.
Really?
Yes.
Nice. Yeah, JavaScript is full of these fun and horrible programming rules. Simon?
I know that in Python there's some special statements that you can do to change the scope of it, or to find the variable or put it into a scope. I know there's one called non-local, which is only useful for like nested functions or something like that. Whereas
Interesting.
The non-local variable gets the variable of like the function above it or something.
Weird. Yeah. Python has tons of weird rules too. Yeah?
I find the way that C handles the static keyword very interesting. To my understanding, is that within a certain function scope, if you declare a static x equals 1 and then increment x later, returning back to that function will remain x at 2.
Yeah, it's like the scope that lives on, right? And static gets very...
It's like a local scope on a global level.
Yeah. Yeah, static gets weird. I don't know all of the rules around static, but definitely weird stuff like that. So scope is interesting. James?
What about concurrent programs, like when you want to synchronize variables? How does that? I'm not sure how to apply.
Yeah, so typically in concurrent programs, when you want to synchronize variables, you end up using memory. And then memory has a global scope, right? Because memory usually refers to DRAM, and all of your threads have access to DRAM. So yeah, it's kind of like we have this notion of scope at the programming level for our variables, but also like at the hardware level, we have this notion of scope at like the memory and stuff like that. So it is pretty fundamental in a lot of areas of the stack. Yeah.
On the topic of that, I think it depends on like which version of like GCC you're using. And from what I've heard with like C, it'll not like if you allocate on the stack from the heap, it'll not be thread safe. If it's like an older version, but newer versions it is, which is kind of interesting.
Yeah.
That's what I like.
Okay, that would be interesting. Yeah, the compilers do all sorts of weird stuff. And yeah, hopefully some of this class will help demystify why compilers do. But if you have a reference for that, you should post on Piazza, because I'd be interested in seeing some of that craziness. Yeah, so, just to like remind ourselves a little bit of some of the scoping rules and see that it can change, we can go play around with some Python scopes. I don't have completely crazy ones, but let's say you have x equals 2, y equals 2, and then, if we want to print y should be 2, right? That's should be pretty uncontroversial. Let's see. Okay, so 2. Now, if we make a function foo, we define foo, and if we print y in foo, this is kind of like a global variable, right? Y is defined out here. What's this print going to do? Are we going to get 2? What do people think? We've all written code like this. 2. So we can have global variables. We have this global scope. what happens if I'm going to print y now. I'm going to print y in foo. I'm going to print it outside of foo. But I'm going to change y. I'm going to say y equals 5. So if we kind of step through this mentally, we're going to call foo. We're going to print y. Y is going to be equal to 2. We're going to reset y to 5. And so we should get 5 here, right? Is that what's going to happen? Many of us have probably ran into this as well. Sorry, saving. That's another error that can happen. We get an undeclared variable. And in fact, we get it at this print statement. So this print statement is no longer working, which is kind of weird because I put something after the print statement and it changed what this above print statement was doing. So what's going on here? Yeah.
It's when you do that, it changes y to be a local variable, locally scoped to the foo function. Mostly just because Python doesn't have a good way to define when something is defined.
Yeah.
So it just assumes that if you're setting a variable that's already been set, you want to create a new one within the scope.
I see. So will this work? I moved the y equals 5 up here.
Yes.
Okay, and what should this print? If life has any meaning, what should this print?
5.
5, yes, because we just assigned it. And then do we get 5 here as well? No, let's see. 5 and 2. So it's like we kind of just by that in Python, by writing to the variable, we've changed its scope. Because now it basically y is local to this function, but then the global y comes back down here. Yep.
Even if Python's line-by-line interpreted, is there a reason why foo doesn't look to the global scope if you can't find something that's local scope?
Yeah, I mean, I think it's because Python does a bit of pre-processing before, and that's how it can determine. Like when we wrote to y, it bound y to. It said don't go to the global scope for y, and instead throw that. I'm not 100% sure on the internals of Python, but it must. You're right, because if it's line by line, when it got to this print, it would have looked to the global one. But it must be doing some sort of pre-processing. Yeah. Here's another one. What if we have like if true y equals 3? So let's make that go away. And let's actually do something different. Let's do z equals 3, and let's print z. So what's going to happen here? Are we going to be able to print z after this statement? Should we try it? Foo is undeclared. Let me just comment that out. So we get 3 there. But I find this test interesting because depending on how the code is executed, it's now going to be undefined. So like we were saying before, we were talking about scoping. Can it be determined at compile time or at runtime? This just shows that, Python requires at runtime because z doesn't come into the scope until this is executed. I also find this interesting because it's different than what you might see in C. So if we had like a C program, if we had something like if true, and we said int x equals 4 or something like that, then like print f %d, something like that, this would fail, and this would fail because x would no longer be in the scope. X isn't in the scope here, but in Python, you can do this kind of assignment, which is almost like declaring a variable, but then it survives the scope of the conditional, and it kind of escapes that and comes outside of it. All of this, I think, is to kind of help you see that scope is not, it seems to be pretty intuitive when we're using it. I'm sure we've all been bitten by scoping issues. And the scoping rules change across common programming languages. And the compiler plays a big part in determining those scoping rules and determining them and then at the end of the day enforcing them. So let's talk a little bit about how compilers do this. So what we're going to do in this class, we're going to consider what's called lexical scope. And for this, again, because C is sort of our North Star, this is what the type of scoping that C has. So if we have a program like this, int x equals 0, int y equals 0, y equals 0 here, plus 1 to x, plus 1 to y, plus 1 to x, and plus 1 to y here, what's the final value of x in this program? See, Jacob? 2. Is that the same thing as the final value for y? No. It's because we get a local version of y here, and so when we increment this y, what happens to that y? At the end of this brace, it just sort of dies, right? And then this y goes to the global scope, so this one becomes 1. So that's sort of an example of the type of scope that we're going to use. In order to enforce the scope, what we're going to use is we're going to use this new object. This object is called a symbol table. It's essentially a way how we track scope. Now, the textbook will talk about many different ways how to implement this. There are lots of ways. We're going to do a pretty simple way. But symbol tables ultimately have 2 methods. One of them is lookup. So it takes an ID, and it essentially looks up an ID in the symbol table. And in our world, it's going to return none if the ID is not in the symbol table. We're also going to be able to insert into the symbol table. We're going to insert an ID, and we're going to insert some info about the ID. Some information that we might want to insert could be the type, could be the line number where it was declared, whatever sort of meta information we want to carry around. So now I'm going to define a very simple programming language for us to talk about scope. Basically, this programming language has a simple ID. It has an increment operator. We have a type. We're just going to have ints. We're going to have L brace and an R brace, and we're going to have a semicolon. And it essentially lets us specify programs like this. Like we can declare a variable, and we can increment it. And we can also put braces around them. So pretty simple programming language, and we're going to use this to illustrate scope. So the question is this program right here should throw an error, right? Because we have x declared up here, y is declared in the inner scope, but yet we refer to y right here. And so, if we wrote a C program like this, we'd throw an error. And what we're going to talk about is how to get this functionality into our compiler so that it does throw an error when something like this happens. Okay, so what we have to do is we are now going to look at what happens in our grammar. So in our grammar, we're going to have something like this, where we have type, ID, semicolon. Very simple to the type declaration statement you have in your grammar. And once we see this rule, once we match this rule, we need to update our symbol table. So what we're going to do is if we're in a recursive descent parser, we can eat the type. What we can do is we can grab the variable name. That's just going to be that next lexeme that we match. Then we can eat the ID. And then what we can do is we can insert into our symbol table. We have that variable name. And in this case, in our simple example, we're not inserting any information. What you might want to do is you might want to grab the type and insert the type information. You can do that as well. Right now, what we're going to do is focus on catching errors rather than storing information. So in a recursive descent parser, as we're parsing, we can pretty easily grab those variable names and put them into the symbol table. Now, if we're going to increment, that's an ID increment semicolon. Again, what we want to do is check for errors. We want to check for scoping errors. So what we want to do is we're going to grab that variable name. So that variable name is going to be that first lexeme value. What we want to do is we want to look it up. So we go to our symbol table, we look it up. And if it is not or if it's none, then we have an exception. And that's the type of exception where your compiler would say, hey, you reference this ID on this line number, but it's not in scope. So that's the exception that you would raise. Otherwise, you keep parsing. You eat the ID, you eat the increment, and then you eat the semicolon. But you can start to see that we're embedding new things into our parser to catch certain errors. Okay, now the question becomes, how do we deal with the braces? Because the braces have certain rules when it comes to scope. When you encounter a left or an open brace or a left brace, we have to start a new scope. When we close the brace, we end the scope, right? So we need to be able to encode that into our parser. What we need now is we need two new methods for our symbol table. So before, our symbol table was able to look things up, and it was able to insert information. What we need now is we need to be able to, what we want to call push scope. So this pushes a new scope to the symbol table. And we want to be able to pop a scope, which takes a scope off. And so in your homework, we will leave this as a exercise for the next week or so. But essentially what you're going to have to do is you're going to have to parse this left brace, then push a scope, parse your statement list, and then pop a scope when you come out here. Laura?
So then the code that we have an example in the last slide, should the X++ give an error?
Let's see. So, yeah, so Y++ will give the error. Because what you're going to, so we haven't talked about how the symbol table is implemented. We've just talked about the API. So we kind of know what it should do. We know the API, and we know kind of how to embed the API into our parser so that we can catch these errors. So if we kind of walk through what happens here, is we're going to insert X into the symbol table, right? We're going to parse this. That's going to push a scope. And then we're going to add Y to the symbol table. And then here we're going to look up X. Well, X is there because it corresponds to that one. We're going to look up Y. Y corresponds to that one. Now we're going to pop the scope. And when we pop the scope, Y goes away. And because Y goes away, it's no longer in the symbol table when we look it up.
So when you say push and scope, it's like on top of the ones we already have.
Yes, so we're going to talk about an implementation in 1 second.
So we don't forget the previous one.
Exactly. So yeah, right now we've just defined the API. We haven't said how we're going to implement this. But maybe some of you kind of have an idea on how you'd implement this. Let's see. So what data structure would you use if you wanted to implement a symbol table like this? What data structures are good at mapping strings? Yep. Hash table, exactly. Just one hash table? Yeah, exactly. So we're going to use multiple hash tables here. And yeah, I put you on the spot, but it's exactly right. We want one hash table for every scope that we have. So, like I said, the book will talk about lots of different ways how to implement this. And 10 years ago, people thought about really efficient ways how to implement these symbol tables. Turns out symbol tables are not the most expensive part of a compiler, so people kind of stopped looking at them. I think a stack of hash tables ends up being a very good approach. So you basically start off with your base scope. That's going to be one hash table here at the bottom. When you push a scope, you add a new hash table to your stack. So your base data structure is a stack, and your stack contains hash tables. So you put a new hash table at the top of the stack. Then when you insert something into the symbol table, you insert it to the top hash table. So whatever hash table is at the top, that's where you insert it. And then when you look something up, what you do is you start at the top hash table. If it's there, that's great. That's what you found. And that's going to give you the variable declaration that happened closest to when you refer to it, because you're at the top of the hash table. If it's not in that hash table, then you go down and you check in the next one. And you keep doing that until either you find it, or if you make it to the bottom and you don't find it, then you have a scoping error. Now, when you pop the scope, you just take that hash table and you just throw it away. What about everything that was declared in that hash table? Where does it go? It's gone. It's no longer in the program. So, this is, we talked a little bit about this. I think we had a little discussion on it last week where, we said statements could just appear anywhere in the braces could just appear anywhere in your code. You can just have braces and, these block statements anywhere, and they just create scope, and then you just throw away the scope when it ends. Yep.
When giving for C, for example, I'm pretty sure for function So in our hash tables, with our parameters, create new entries into our hash tables.
That's interesting. Like, so if you have a function, you have your parameters, and they should go in your symbol table because you can refer to them, right?
If my function's just add and I have the parameters x and y, and there's an x outside the scope, and it's 2, I believe it creates a copy of 2 and uses the x parameter inside the function.
So are you saying if there's a global one and a parameter, if there's a name collision?
Yeah, if you use that global one as when you call the function.
When you call the function, now it's sort of becoming a spaghetti bowl. So you call the function with the global one, and then you map it to a local one. I mean, ideally, you're going to search the hash tables from top down. And your global variables all live in your bottom one. And this is why if you have never been bit by a global variable bug, you will get bit by them, because if you think you're referring to a global variable and if you have something locally, then you'll catch the local one first. That's the one that it'll end up referring to. So, just think about it in terms of this stack of hash tables, and whichever one has the closest declaration is the one you're going to catch. So global is at the very bottom, then your function parameters are going to be your next one up, and then any braces, if statements, for loops, whatever, are going to kind of go on top. Yeah, good question. Yep?
Are we going to be adding functions to our CSS tool? Or is that not? Because right now it's just functions.
No, we will not do functions in the end. They get a little bit hairy, as you can kind of imagine. But you can think about how, like this whole time, I think you should think about how you would extend it to do interesting things like functions. Yep. We will eventually have function headers, though, so that'll come. Okay. So just to make sure that everybody kind of understands this, let's walk through that top example that we had, and let's see if we can let's see if we can figure out that final value that we have in x and y like we asked at the very beginning. So if we step through this, let's see. So if we do this line, x equals 0, we think about, as we're parsing it, we're going to catch this. And if we kind of wanted to interpret this in our symbol table, what would we do here? Well, we have x. We need to put x into the symbol table. And let's say that we're interpreting this language as well. So we're going to store it along with the value. So we're going to have x, 0. We're going to put that in our base hash table. Next, we see y equals 0. So again, we're going to put that in the base hash table. Then we parse this opening brace. What that means is we need to push a hash table. So we get a new hash table up here. Then we get this in y. So I think this is a little bit interesting here, because we actually have some choices. So this is OK in C, right? We could write this code in C and it would be OK. But if you're designing your own language, kind of seems to me that maybe you don't even want to allow this. Like, if you're making your own language, you get to make the rules. And what you do is when you parse this statement, what you could do is you could go see if y is declared somewhere else, and potentially you could throw an error here. If we're using C as our North Star, then this is allowed, but the world can be whatever you make it. So we have this here now. So now when we increment x, we first look in our top hash table. We don't have an x, so we go to the one lower. And we do have an x, x++. That means the value for x is 1. Next, we parse this line, y++. And if we have y++, we start at the top hash table. We do have a y there, so then this y goes to 1. We close the brace, which means we pop the scope. So sadly, this all dies and goes away. Next, we do x++. We just go look at our single hash table. That means x is equal to 2. And then y++, we just have the base hash table, and we do y equals 1. So you can see how the stack of hash tables and pushing and popping the scope, ultimately I think conceptually I don't think this is super complicated, just a stack of hash tables. But it really allows us to to do scope, interesting things with scope, and basically do scope essentially how C and C++ do it. So I think it's pretty interesting. Okay, so that sort of finishes up the conversation with symbol tables. You're not doing symbol tables for this homework. You will do symbol tables for the homework that's coming out tonight. So be ready for that. We got about 5 minutes, but I'll let you get that time back to go work on your homework. So thanks, everybody, and starting Module 3 next time.